All right, so here's our problem. Excuse me. We're told that, let's see if I can make this a little larger. Okay. Fairfield Automotive is the local dealership selling Honda automobiles. Honda owners average more than 85,000 miles before trading in or selling their Hondas. To test this, an independent agency selected a random sample of 18 Honda owners who have either traded or sold their Hondas and determined the number of miles on the car when the owner parted with it. It plans to test Fairfield's claim at alpha is 5%. That means we want to restrict the chance of committing type 1 error to 5%. All right? What was type 1 error again? If you reject the null hypothesis when it is true. Exactly. Okay? State the hypotheses. If the sample mean is 86,200, right, and the standard deviation is 12,000 miles, what conclusion can be reached about the claim? All right? So they're claiming that they traded at somewhere about 85,000 miles. The sample evidence is showing 86,200 miles. So just based on the sample evidence, it's suggesting that it's different, correct? But is there enough evidence? So what do we need to do? We need to measure it by looking at the sampling error. Am I right? The difference between X bar and mu. Right now it's only looking like 1,200. Is that enough to say that it's different? Let's find out, all right? So that's why we go through the formal steps and so on. I'm going to continue working here on my iPad. And so, here we go. I'm just going to bring up the, so let's use this then. 80, and then we are 86 to show that that is indeed the case. Yep. All right, so what conclusions can we draw? So the information that we had was there's a belief that people, they trade in, owners trade in at 85,000 miles. Okay? So we had a sample taken, N was 100. We got a sample mean of 86,200 miles, and we're told that the sample standard deviation, S, was 12,000 miles. Okay? So the first thing we need are the hypotheses. Now, to state the hypotheses, we establish what our null hypothesis is first. What our alternate hypothesis is first, and then the opposite of that is our null hypothesis. So I'm going to do step 1. Hypotheses. So I like to start with HA first, which is the alternate, which is what we want to prove, and HO is what we will assume is true, all right? So HA, what we're going to try to prove, we're not going to try to prove that it is 85,000. We're going to try to prove that it is not 85,000. In other words, it's different, all right? Because you can never prove from a sample that the population parameter is an exact value. You cannot do that. The only way you could prove an exact value is if you have the entire population. So we are not going to try to prove that the mean is 85,000. We're going to try to find evidence it is not 85,000. and the sample evidence seems to be moving slightly in our favor, but we don't know if it's enough evidence, right? So I like to start with HA, which is that the mean is not 85,000, which means we will assume that it is 85,000. So HO is what you assume is true. HO, the mean is 85,000. So that's step one. I really should put it in words for you as well, I should say. In words, this would say something like this: average mileage at trading is 85,000 versus the average mileage at trading is not 85,000. So one is exactly the opposite of the other. Remember that, okay? And then, yes, please.
Why would we say like E was greater than?
Oh, because we were not asked to test that it was greater, right? We just asked to test the claim. What's the claim? They're claiming it is 85,000,
Okay.
right? So opposite of that is it's not 85,000. If they'd ask you to find evidence that it is greater than 85,000, then you would put that, right? Okay. But right now, we just need to test it's different from 85,000.
Okay.
So that's the first step. Second part. So that was our hypothesis. Number two, test statistic. Now, we said the test statistic is how we measure the evidence. And we will measure the evidence by converting the sampling error to standard deviations. So, we know Z is standard deviations. We know T is standard deviations. Should I be using Z or T?
T.
T, tell me why.
We don't know sigma.
Sigma is unknown. Exactly. Okay? So we're going to use T. Usually we try to avoid T first, but hey, we're going to start with T. By now you know how to use it. So T is equal to X bar minus mu S over the square root of N and the degrees of freedom N minus 1. All right? So that's our test statistic. The decision rule. Three. And that's where a lot of people have difficulty. So we're talking about a T distribution, so we'll do this. Now, for us to know if we have, when we setting up the rejection region, we need to know if it is a one-tail or two-tail problem. Meaning, do we have rejection regions in both tails or one tail? So, the question you will ask yourself is, to reject the null hypothesis, where should we look for evidence? And always look for the evidence in the tail. Because remember, it's extreme values we're looking for to reject the null hypothesis, correct? The values have to be extreme, which means they take us into the tails. They don't take us into the middle. The mangoes are not, we don't want the mangoes sitting around the middle. We want the mangoes in the end to reject the null hypothesis. So, when you look at this question, what kinds of values will reject HO for you? Just give me an example. Just fraud value.
Less than 85 and
More
more than 85.
than 85 or less than 85. So like, if I had 82,000, that's evidence it's not 85, isn't that right?
Yeah.
If I have 88,000, that's also evidence that is not. So in this case, we could look for the evidence in both tails. Which case it becomes a two-tail test. Go ahead.
What's under the mean? Is that 0?
Yes, that's the T distribution.
Okay.
Yeah.
Is it always two-tail or it can be one-tail?
No. Depends on the problem. So how you know, and I like people to reason it out rather than just looking for shortcuts, but here's how you know. If you are testing the mean is not equal to something, two-tailed. If you're testing the mean is greater than something, or the mean is less than something, one-tailed. Okay? So how do you know? Because for two-tailed, you get evidence in both tails. If I want to prove that the mean is greater than a value, I'm looking for evidence in the right tail. Let's look at the head, the arrowhead. If I'm looking for evidence that is less than a value, I'm looking for evidence in the other tail. So those two are one-tailed tests, this one is two-tailed test. Okay? But you need to be able to explain it to somebody. Your grandmother's walking down the street and she says, I heard about this two-tailed testing. What's that about? You know, you got to be able to explain to your grandmother. Okay? So, in this case, that's my rejection region. So if my test statistic falls in those regions, I'll reject the null hypothesis. Reject HO, reject HO. All right? Cool. So how do I determine what these boundaries are, my fences? I need to determine that. What helps me with that? Alpha. So the total area that I could commit type 1 error must be equal to alpha. Since this is symmetrical, what's the size of each tail? Absolutely. You got it. Thank you. I like when people are responding. So 0.025, 0.025, okay? The degrees of freedom would be 79. So to find our critical values, we call those T alpha over 2 degrees of freedom is T 0.025, 79. That's a positive one, and this one will be the negative one. Let's go to the T table. Anybody have the T table? I don't want to switch back and forth. So go to the T table for me, please. Look for 79 degrees of freedom and 0.025 in the tail. Give me that T value. Maybe 1.7 something, maybe? 1.68 something?
So 1.99.
Oh, 1.99. Oh, 0.025. Yeah. That's right. It's close. It's like having a 95% confidence interval. So 1.96 if it was Z, but because it's T, it's going to be bigger than that. So this is 1.99 what?
0.
Perfect. Negative 1.990. So those are our critical values, all right? So our decision rule is as follows. The rule, reject HO if T, now I'm going to put the absolute value of T is greater than 1.990. Why did I write it that way? Because I don't want to put, if T is less than negative 1, T is positive, right? Take the absolute value of T, and if it's greater than 1.990, we reject the null hypothesis. Everybody understand that? Yeah? Understand that? Okay, like I said, I can put it in two parts. If T is less than negative 1.990, or T is greater than, so just take the absolute value of T, the 1.99, is greater than 1.990, then we're good. Okay, that's the decision rule.
Sorry, I don't get that.
What's that?
What you just said.
Okay, so if I wanted to write it out fully, I would have said, if T is less than negative 1.990, or T is greater than or equal to.
Yeah, that's not what I was thinking.
Right, but I'm just saying you could shorten that by saying the absolute value of T is greater than or equal to 1.990. Absolute value is always positive. To reject the null hypothesis, yeah. Reject HO. Did I say reject HO? Yeah, reject HO. All right, so that's just a shorter way to do it. You see? How many characters he says? Yeah?
To me, it doesn't make sense, but I'll do it the other way.
Okay, no problem. It's fine. You can do it that way. A two-tailed test, you could write both of them.
Okay. Yeah.
Or they say the absolute value must be greater than. Okay. Now let's go to our analysis. Once you get the first 3 steps correct, you should then be able to solve this problem. Step 4. Analysis. So T is equal to 86 minus 85 over 1,200. 1,200 or 12,000? 12,000 divided by the square root of 80. Somebody find that for me, please. Something for sure.
I got 0.894.
0.894? Anybody else? I thought you might get 1 point something. I could be wrong.
I'm going to redo it.
Oh, no, you're right. No, you're right.
Oh.
Because I was multiplying by 10. There's 1,200, and I multiply by 10, 12,000, but the square root of 80 is less than 10. So it's be point something.
0.89?
0.89. Okay, all right. So T is equal to 0.890, I'm assuming, or whatever. 44, okay. Excellent. So you can see from the evidence already, it's not recording. So now, this is, as you can see from the evidence, it's not enough. But let's do something. Let's find a p-value. What is a p-value? It's interesting now. So the p-value, so basically we could actually finish this problem by just comparing this value with the 1.990, correct? And as you can see, it didn't travel far enough to be an outlier. Okay, it didn't travel far enough. It only traveled 0.89 standard deviations. How many standard deviations must it travel to be considered an outlier? 1.99 standard deviations. Almost 2 standard deviations to be considered an outlier. So it's not sufficiently different from the mean to be considered an outlier. So that's why we're not going to reject the null hypothesis. Make sense?
We failed to reject it.
We failed to reject the null, okay? Now, I want you to go one step further and not just compare this value with the critical value, but to look at it as a probability. What's the likelihood? Remember I asked you, what's the likelihood it will snow in July? So basically, that's taking the event and attaching a probability to it. What's the probability that apple would be all the way over there? So now let's go that one step further and measure it in terms of probability. We get the same answer. But one compares standard deviations, the other one will compare probabilities. So I want you to start thinking in terms of probabilities. So let's do that. So with the t distribution, it's usually a little bit different, as you know. So the p-value is basically the probability of finding that kind of evidence that we just got. Because there's 2 tails, positive 0.8944 is equivalent to negative 0.8944, correct? So our p-value is given like this. Let me see how if I show that to you. Let's use a different color. Let's use green. So this is hang on. Here, this is green. This is 199, negative 1.99. But let's go blue, 0.8944 negative, and 0.8944 positive. So negative 0.8944. So as you can see, these 2 values are inside of the safe do not reject region. But the probability of observing that kind of evidence is this area right here, the green area. This one plus that one, right? That's a probability of observing that kind of evidence. All right? So let's find it. We know we know the value of the t. We have the degrees of freedom. Let's find what areas those are. That's called a p-value, but because it's only half of it, it's p-value over 2. And this is the other half right here. Oops. Well. So p-value over 2, half of the p-value is here, half of the p-value is here. In much the same way as half of alpha is here and half of alpha is over here. So what I need you to do for me, you're not going to get the exact value. Look in the t-table, look for under 79 degrees of freedom, try to find a 0.8944, as close as you could get to it, and then go up and look at the area in the tail. Since you're not going to get it exactly, you're going to have to bracket it between two values. Like it might be between 10% and 5%, or between 20% and 10%, or something like that. You see that? Yeah. Okay, so give me the two values that bracket that 0.8944.
0.20, 0.10.
Okay, I thought so. So for p-value, the p-value will be given by the probability that t, because we're talking about a two-tailed test, I could write it out for your sake. I could write it out in two parts. So it would be the p, t is less than negative 0.8944 plus p, t greater than or equal to 0.8944. It's in both tails. Or I could just do this, which is the same thing as p, the absolute value of t, greater than 0.8944. Right? But I must multiply it by 2, because there are two of them. All right? So that would be 2 times, and we know that half of the p-value is between, you said, 20% and 10%? Okay. So twice that would be that the p-value is between 0.4 and 0.2. That's the p-value. So the decision rule is that, which is in terms of p-values, if your p-value is smaller than your alpha, you will reject the null hypothesis. If the p-value is larger than your alpha, you will not reject the null hypothesis. Remember, our alpha for this, our significance level is 5%. This p-value is between 40 and 20%, so it's much bigger. So we will not reject the null hypothesis. You get exactly the same answer. But one looks at it in terms of probabilities, the other one looks at it in terms of the critical values, right? The exact same answer. Now, I will help you understand how to interpret this p-value a little bit after that. Let me just finish this off, step 5, okay? Because I know that most people don't get it right away. In terms of the relation, when we compare the probabilities, most people don't get it right away. So, 5, our decision and our conclusion. So we'll say since 0.8944 is less than 1.990, we fail to reject HO. All right? That's basically called the classical approach, or when we're comparing the critical values. So this is called critical value approach. It means that we're just comparing the boundaries, right? So that's when you're comparing your critical, your T critical with your T value or your Z critical with your Z value. If we're doing the P value approach, or we could say, since the P value is greater than 0.05, we fail to reject HO. Okay? We fail to reject HO. And then there is a possibility of type 2 error. Failing to reject the null hypothesis when it is false. Possibility of type 2 error. So type 1 is when we reject the null hypothesis. Type 2 is when we don't reject it. Right? So, let me help you understand the p-value approach a little bit. So in the example that I did earlier when we were starting to introduce this topic, and we had gotten a Z value, I think it was a T value of 10, right? That one there, we said, oh, the probability of observing that sample is almost 0. Remember that? So, another way of thinking about a p-value is, what is the risk that you're taking if you reject the null hypothesis? Because in order to reject the null hypothesis, you have to, be considered an outlier. So if I'm considering this an outlier, how much risk am I taking? The actual risk in probabilistic terms is the probability that we associate with it. In that case, it was 0. So how much risk am I taking if I reject the null hypothesis? In that case, it was almost 0. All right? Now, in this example, if I want to reject the null hypothesis, how much risk will I be taking? The risk is always the probability associated with the sample. What's the risk I'll be taking? Between, what is it?
40.
Between 20 and 40% risk, okay, of being wrong. What alpha does for us, folks, is limit how much risk we should take. How much risk did alpha say we should take? Maximum amount? 5%. But if we reject the hypothesis, we'll be taking 40%, between 20 and 40%, which is much more than what we allow. That's why we do not reject the hypothesis. So the p-value approach basically allows you to compare the actual risk associated with the sample and a limit that the problem gives you. Okay? So typical levels of risk is like 10%, 5%, 1%, 2.5%. Just like confidence intervals, 9. So those tend to be the typical risk levels. Okay? So in this case, according to that example, we will be, if we reject the null hypothesis, we have to be real gamblers, taking between 20 and 40% risk of being wrong. Right? But you're told, don't take any more than 5% risk. So we will not reject the null hypothesis. Okay? So I want you, if you get that correct, then you put it down. Okay? So, let's recap. 5 steps. State your hypotheses. Alright? I always start with what I want to prove, which is my alternate, and then I work backwards. The null. Always remember the null has the equal sign in it. Always remember that. Remember that, always have the equal sign. Because what happens is when you're doing the test, you have to set the value to something. You have to say, let's assume it's that. So if we're going to assume it's a particular value, that means that your null hypothesis has to have the equal sign. Okay? Let's assume that it is 500. Let's assume that it is 85,000. Then, what's my test statistic? If I had given you sigma was 12,000, you'd have used what? Z. So because you don't have sigma, we use T. Alright? Absolutely. So, now that we know our test statistic, remember our test statistic is measuring for us just how wide or how big the sampling error is. If your sampling error is small, then we say that's no different from the population, so that's okay. But if it's big, then you say that's very different now. Okay? So establish a test statistic. The decision rule will be based on us telling you how much risk to take. So that's where alpha comes in. If you're not given alpha, most people say, well, what do we do? I don't know alpha, right? You look at the p-value, and then you say, how much risk am I going to take? I'm not going to take more than 10% risk. And then you compare it to that. But for our purposes, we give you alpha all the time. In real life, nobody's coming over to show that if you're working for a company and you're doing a research project, alpha's 5%. Nobody's telling you that. You have to look at the data and say, p-value associated with that sample is 25%. Nobody's taking 25% risk. So, but through your statistics exposure, you say, well, typically we take 1%, 2%, 5%, up to 10%, right? And so you decide that for yourself when you're out there. Then, once you have your significance level, you set up the boundaries by putting the critical values associated with those two. With alpha, and then you gather your evidence, you find the probability, you find the T or Z value, and then you compare it. So if you compare the critical values associated with alpha to your T or Z value, we call that the critical value approach. If you now go one step further and say, what's the probability associated with that sample? Then that probability compared to alpha gives you the p-value approach, okay? And remember the p-value approach, you want to take less risk than alpha. So if your p-value is less than alpha, you reject the null hypothesis. If it is not, you fail to reject the null hypothesis, all right? Any questions? We don't even have time for you to do an example. So, because introducing hypothesis testing takes a little time, all right? And I know you didn't have time to fully watch the videos, but when we meet again, I'm going to be popping a question at you right away. So we're going to proportions, and proportions is exactly the same 5 steps, but the test statistic will be what? P bar minus
T.
That's it. That's the only difference. Same 5 steps. Okay?
With the p-value and the critical value are not
No. They give you exactly the same answer. If you get 2 different answers, you made a mistake somewhere.
Yeah.
All right? Because one is just like, say, 15 inches.